thanks for the introduction and the opportunity to present the work here at this great workshop. And today I'll be trying to introduce and to present a set of works that started during my PhD in Torino, Italy, with Hodge, who was a postdoc there and now is at MIT, and a very recent work that we were able to push out on the archive in August, together again with Algebraic and Robin Schneider, who I see he's in the participant list. So I think he'll be very glad to answer any questions, since he's definitely more expert than me in the most mathematical sides and matters of the work. And finally, together with Mohamed Tamazousti of the CEA list here in France, where I'm currently based. The plan of the talk is to first introduce a bit the scenery. So I'd like to introduce the problem that we are trying to address and the way we are trying to address it through machine learning and deep learning approaches. And I will try to show you how we were able to actually merge an algebraic geometry problem into a computer vision related problem, and how actually research from Google helped in shaping the problem and trying to solve it. The first thing, of course, is to set up the stage. And basically, our problem originates in string theory, which, as you know, is a quantum gravity theory defined at a very, very high energy scale in a 10 dimension, whose ultimate goal is, of course, to find the standard model of particle physics, meaning that basically string theory would be able to explain the physics as we know at present energies in some way, and being a UV complete theory. However, the problem of reducing from a 10-dimensional high energy theory to an effective theory of physics in 4 dimensions is pretty complicated, because there might be only one model that actually models particle physics. But the number of possible theories, of possible effective theories, is actually huge and shaped in a really complicated way. So basically, the problem stands in the fact that the dimensional reduction to 4 dimensions is actually complicated by the presence of a lot of possible choices, of possible models from which we can actually choose, and we basically find ourselves in front of a barrier of possible models and choices that prevents us from finding a unique 4D effective field theory in a direct or in a very simple way. Just as a small advertisement at this moment, there is actually an alternative to do to this particular procedure and this dimensional reduction, which is to build an explicit string field theory. And I would just like to point out that Harold's book was actually published very recently and presents a very nice introduction to modern string field theory, with also some computational challenges explained and presented in detail. So coming back to our original problem of finding the standard model of particle physics, we need to learn how to deal with large numbers and large quantities in physics. And this is because this is actually explainable in a lot of ways. So, for example, from the most analytical problems, because, for example, we could go through a lot of possible choices that we have to make. And, for example, if we were to consider all the possible compactifications that we can do in F theory, we would find a huge amount of possible vacua from which to choose. But even from just enumerating the number of polytopes in the process list, for example, we would find a huge number of possibilities to choose from. We also have a lot of problems which are more computational, because in general terms, typical problems that we encounter are mostly NP-hard and undecidable. And also there is no actual a single framework to handle all flux compactifications that we find in string theory. That means that in general, in the string theory community, people have tried a lot of different approaches, from analytic computations, from the very few examples that we are actually capable of computing, to random scans, or even just enumerating all the possibilities that we have. So in general, the problem is very diverse, and there are a lot of possibilities to tackle it in a different way. So in a sense, what's best for us, and what I would like to explore with you today, is the fact that we also have an alternative. So we can try to do more exploration rather than finding a solution from the analytical point of view. So our intention is, alongside the seminal paper that came out in 2014, where the non-deterministic search methods that were actually mentioned in the paper are geometrical algorithms for the exploration of the string theory landscape. So that basically presented a very first example of what exploration can do in string theory. So exploration would mean to basically exchange a very difficult analytical problem with an optimization problem of a non-deterministic search method, which it's not simple, but at least it's feasible, and from which to try to retain better generalization properties, to be able to try and see if patterns come up, or if there are any directions in which to explore the landscape. On the other side, we might encounter some problems in finding black box models, meaning that we might find models which are very difficult to interpret, and that might be a problem when we want to find actually an analytical formula from an exploration algorithm. For this, some explainable AI systems have been devised and might be very interesting to use in this for the exploration of the string theory landscape. The goal for today is thus to try and study a very particular problem in string theory, and in our case would be to compute the Hodge numbers of complete intersections Calabi-Yau manifolds, and trying to do it at the intersection of physics and computer science, basically merging what we know from the geometric data that we have, so basically using information from string theory and algebraic geometry, and connecting them with knowledge from computer science, and in particular from AI models coming from computer vision and object recognition. This way, we basically want to tackle the problem from a deep learning point of view, but not just deep learning, but also, but in particular, a geometric formulation of deep learning, in which basically the architecture can be modeled starting from knowledge of the underlying theory that we have, but also without adding mathematical information inside the architecture, basically letting the model come up with a solution by itself. The starting data from which we start our exploration is, of course, data which come from a physical knowledge, that are also relevant algebraic geometry objects. And they come from the fact that when we compactify on a certain manifolds, the 6th extra dimension of string theory, we have very stringent constraints on the kind of manifold that we can actually use. So, for example, our manifold X should be compact and should break most of the supersymmetries in 4 dimensions in order to be as phenomenologically plausible as possible. And by phenomenologically plausible, I mean it must contain the standard model gauge algebra inside the gauge algebra, which remains once we do the compactification. These objects have been postulated and proved to exist. They are called Calabi-Yau manifolds, and in the particular case of a 10-dimensional string theory, they are complex manifolds in 3 complex dimensions with Ricci flat properties, or conversely, a vanishing first Chern class. The problem for us and for string theories is the fact that there are no metrics for compact Calabi-Yau. Hence, the direct dimensional reduction that we all hope for is not possible. We then revert to the study of topological properties of these Calabi-Yau manifolds. And the reason is that a partial information or even some information on the 4D phenomenology is actually hidden inside topological properties. And in particular, the complex dimensions or the cohomology groups or the Calabi-Yau manifolds are actually extremely important for the string theory, giving, for example, information on the generation of fermions or the kind of particles and their interactions in the 4D phenomenon, in the 4D effective field theory. These, of course, are known as Hodge numbers, and they will be the object of the study that I will try to present. However, enumerating all the possible Calabi-Yaus is in fact extremely complicated, and we actually try to study a very particular set of Calabi-Yaus in order to study the feasibility of such an approach. And the simplest way to actually build a Calabi-Yau manifold is to create it as an intersection of a certain number of hypersurfaces in a certain number of projective spaces. These are in fact called complete intersection Calabi-Yau manifolds, and they are basically a perfect benchmark for AI in string theory and our approach. The reason is that as we are interested in them from a topological point of view, we do not really retain all the information on the embeddings and on the properties, but we are actually interested mostly in the degree of the defining equations and the possibility to actually generalize to K hypersurfaces and projective spaces basically produces a matrix of K by M entries, which are natural numbers. Of course, they must respect a certain number of constraints. For example, in order to ensure the vanishing of the first Chern class of the matrix. This particular matrix is known as configuration matrix, and it's actually the starting point from which we try to use machine learning and deep learning in order to compute the Hodge numbers. Basically, what we are trying to find is definitely a map between a space of configuration matrices and a space of integer numbers. And this can be done for several kind of Calabi-Yau manifolds, starting from what's more relevant for string theory. So Calabi-Yau manifolds which are 3-dimensional, 3 complex dimensional. But we can also go towards a 4-dimensional Calabi-Yau, complete intersection Calabi-Yau, which are definitely more interesting. In the first case, the job is actually simpler, both because the number of configuration matrices is extremely reduced. It's a very small data set with just 2 learnable Hodge numbers, and a certain number of favorable embeddings. And by favorable, I basically mean that at least the first Hodge number is very easy to compute. In fact, the H11 in a favorable configuration is directly equal to the number of projective spaces defining the Calabi-Yau manifold. Let me point out that there actually exists a data set containing most of the favorable manifolds in 3 dimensions, but for the sake of this seminar, I will actually forget about it. Basically, because the most interesting result actually comes from the case in which the Calabi-Yau threefolds are not in a favorable configuration. Exactly as it happens, for example, the fourfolds, in which we have a lot more available data, almost 1 million configuration matrices, and 4 Hodge numbers to learn, and actually only a slightly more than a half of them in a favorable configuration. Just to point out what we are actually trying to find, we are trying to basically reproduce very different distributions of Hodge numbers, in which I would like to point out the presence of a lot of outliers, and in particular very different ranges of variation of the Hodge numbers. In particular, we can see that in both cases, for the threefolds and fourfolds, H11 is actually almost a Gaussian distribution, so it might be quite easy to learn. But all other Hodge numbers become very, very complicated, and it's actually quite a challenge, even from a deep learning point of view, to learn them properly. The map that we want to find in our study is thus replaced, in our case, by a neural network, parameterized by a certain number of weight theta, and whose learning objective is to minimize a certain loss function. And I'm not specifying at the moment the loss function because it is a central problem in this particular case. And let me just anticipate a bit what I'm going to show later. The idea is to use computer vision method. So basically, the idea is to directly feed the neural network with the configuration metric as if it were an image, as if it were an image competition well known in the computer science field, such as an image net or other kind of competitions that basically study computer vision models. So our approach is actually multifaceted, and it's actually based on data science, because as it was pointed out yesterday in this workshop, one of the important points for deep learning and machine learning approaches is to actually know and to actually formulate well how the training data and how the data set that we use are. For instance, we should never just apply an algorithm to the configuration matrices, but it's fundamental to actually try to do some data science on that in order to find possible properties to exploit in the modeling of the algorithm. And for instance, in this particular case of Calabi-Yau threefolds, we actually performed a lot of feature engineering in order to come up with all the possible information that it was contained inside the configuration matrices. This basically led to a huge list of possible variables that we can study, including some variables which have not a direct relation with algebraic geometry, such as clustering or PCA properties. And this was actually extremely useful in coming up with a solution. For instance, let me point out that the configuration matrix in this particular case is not as important as, for example, its PCA version. And that is actually computable through gradient boosting algorithms or random forests. And it's very important it's a very important study preliminary study before doing deep learning. This basically opens up the possibility to finding the best possible algorithm in order to predict the Hodge numbers. From this kind of study, we actually retain a lot of notable information. And in particular, it seems that in order to predict the Hodge numbers, only a few characteristics are actually important. For example, in this particular case, the projective spaces or their relative dimensions, and in particular, the role of PCA was extremely important. The results were actually the results from a shallow machine learning, so let's say an old version of computer vision applied to the configuration matrix, actually shows that once we retain this information and we actually discard the matrix, we are already able to improve our results even just by a simple linear regression on the data sets. But we can also try to come up with a way to generate these kind of features in a more organized way or even in an automatic way. And one possible solution is to use neural networks, and this is exactly what we are going to do in both follies. And the first possible option is to choose from is a multi-layer perceptron. And the idea is basically that of a feed-forward network in which the following layer is actually simply first a linear map and then a non-linear activation function applied. It has a lot of nice properties, such as being a universal approximator, which basically means that given enough units and enough layers, we should be able to approximate almost any continuous function, any continuous and highly nonlinear function. On the downside, this is actually a black box problem. But let me point out some works which were able to start the field of a duality between neural networks and, in particular, quantum field theory, or not quantum, just field theory. They were actually started by Halverson and others, and it's actually a very recent field of research, and it's actually also very, very active. At this point, once of course we need to choose our training set, set some parameters for the training, and the procedure then involves a lot of trial and error. However, since we are working with geometric data and we are not working with industrial data or data coming from unknown sources, we can use the knowledge that we have on the underlying theory in order to build the model. Let me point out a few previous results in the prediction of Hodge numbers on Calabi-Yau manifolds. And because both 3-folds and 4-folds were actually already studied. And the results here are for a fully connected network applied directly to the configuration matrices. And yeah, we can see that, of course, using deep learning has already improved a lot the accuracy of the predictions. We can, of course, also come up with some data augmentation strategies and data diminution strategies. And for example, in a recent work by Hay, it was very nice to see an approach using fully connected networks and conditional fully connected networks, which are basically neural networks which have two branches in order to do the data augmentation and training. And that actually led to an increase in accuracy, and they were actually a good inspiration for what we have tried to do. Our approach, however, is slightly different because we basically root our work in computer vision and convolutions. Convolutions were introduced in computer vision back at the end of the 1980s by Jan, and they present a lot of nice properties that we can use in order to predict the either a class or, in our case, the Hodge numbers. In particular, they have a locality property, which is very interesting because basically by sharing the parameters inside the networks and sharing them inside a limited portion of the original image, might actually detect some features and apply the same filters in order to research the same features around the image. This is actually an interesting feature for the Calabi-Yau manifolds, because basically by applying the same operations for groups of entries inside the configuration matrices, we might be able to detect patterns inside the network, and possibly we might also be able to come up with a possible analytical interpretation of the patterns that we actually detect through convolution, which is actually very difficult to do with a fully connected network where each pixel of the image, or conversely, each entry of the configuration matrix is actually connected to a totally different weight. This way, we basically reduce the risk of overfitting the network, and we also come up with a way to restrict the information only to the relevant portions inside the configuration matrix. This is done by choosing an appropriate kernel size, which basically aids in picking up larger or smaller pieces of information inside the configuration matrix. One important point that actually came up when we were first tackling the problem is also the fact that the configuration matrix presents a series of symmetry, or rather does not present a series of symmetries, which are usually connected to convolutional neural networks. And one of the points is the fact that the configuration matrix is not invariant under rotation and translations, while notably models using convolutional neural networks are. However, in order to solve these, we did not use many of the operations that are actually common in computer vision, such as pooling, max pooling or average pooling, which are actually the operation that ensure such invariances. This way, basically, our model does not implement rotational translation invariance, but only translation equivariance, which basically is a first example of how knowledge of the underlying theory can actually shape the way we choose an algorithm which comes from a totally different subject, such as computer vision. We basically shape the problem, as I was saying, as a computer vision, and we feed the network with a black and white image at this point. The idea is to learn patterns in an easier way, possibly, and basically we do it in a way in order to encode all the geometrical information that we have in the coming from the data set. The inspiration that we had comes actually from Google researchers, who in 2014 introduced a a new model which actually won the ImageNet competition at the time. And at the time, it was totally new, totally unprecedented, because the underlying idea is to have several different convolutional operations happening at the same time, propagated through the layers. This basically gives the network the ability to choose and to weigh in a different way different features, which are extracted from the original image at different sizes. So basically, the network at every layer can choose whether a more refined or a more coarse feature is actually needed for the prediction. And this is actually what we also want to solve the algebraic geometry problem, because basically we want to see whether the configuration matrix holds its information in a very localized way or more in a coarse-grained way. And in fact, the data science study that we performed at the beginning is actually extremely important at this point, because one thing that we saw is, for example, that the most important roles were played by projective spaces and the dimensions of equations, and also that this is possible to see, for example, through PCA. We also saw that, for example, a larger portion of the entries actually led to better performance. This translates in a computer vision model in using larger kernels, for example. The larger, the better, in a sense. Moreover, it's possible to show that, of course, the Calabi-Yau hypersurfaces contained in the complete intersections are not entirely independent, and thus, basically, the shared informations needs to come up at some point, and this is, of course, embedded also in the convolutional neural networks that we use. And finally, as I was mentioning, the various invariances that we find can be embedded in the model, for example, without using a pooling operation, which, by the way, is also motivated by the fact that we work with matrices which are at most 12 by 15 pixels in the Calabi-Yau 3-folds or 16 by 20 in the Calabi-Yau 4-folds, meaning that pooling operation would actually reduce the information too much for the model to actually be able to predict something. The model that we came up with for the Calabi-Yau 3-folds thus has two concurrent kernels and a concatenation model right after them, such as in the Inception model. The difference is that we actually shape the kernels in a very different way. Instead of having a squared 2D kernels, we actually try to have 1D kernels of the maximal size. Basically, each horizontal kernel spans the variables inside an equation defining the hypersurfaces, while each vertical kernel spans all the equations defining for a certain variables defining the Calabi-Yau. So basically, we use the knowledge of how the configuration matrix is defined in order to build the kernels accordingly. The model is actually very simple. It's also very small because it only has 3 layers. So I wouldn't call it a deep learning model, but it's already enough to make accurate predictions. Here you have a schematic of how the Inception model that we used inside the model is actually functioning. A key role is also played by the batch normalization layer that we have at some point, to which I will actually return in the end of the seminar because it plays an important role. The network actually reaches a very good accuracy pretty fast, because even with just 30% of the data, basically we get 97% of accuracy on one of the Hodge numbers. But the network is also robust enough to be able to predict both Hodge numbers at the same time, at the cost of a bit of accuracy, but also at the cost of overfitting completely the distribution of H1, which is also the most difficult to learn in the Calabi-Yau threefolds case. In our case, we also tried a particular policy on how to choose the training data. And the idea, our idea was to remove the outliers of the distributions from the training set, but retaining them in the test set, in order to avoid learning extremal configurations. So configurations with very high Hodge numbers, but the network was able to actually learn how to extrapolate them consistently. That was actually one feature of the model, which we were very happy to see, and which actually leads to basically 100% accuracy when we use more data for training, 80% of the training data. And in particular, we saw that the particular shape of the kernels is actually extremely important for the task, because it's actually the main element that led to the increase in accuracy. And even more interestingly, the use of 1D kernels for a regression task, as we are doing, because the network in this case is trained in order to approximate a function predicting the Hodge numbers, not just a classification of Hodge numbers. But nonetheless, our Inception network for Calabi-Yau threefolds actually performs better in regression rather than classification, which is usually a simpler task to tackle. Also, another thing, we also tried to compare with other convolutional neural network architectures, such as a more simple ConvNet, using just one convolution for the entire model. And we saw that the other important element that brought to the increase in accuracy is actually the presence of two different convolution operations happening at the same time before a concatenation. So basically, the fact that we are able to scan each projective space for each variable and each variable for each projective space in two different operations is actually approximating the values of the Hodge numbers almost optimally. The next step is, of course, to consider Calabi-Yau fourfolds, which basically enhance the problems that we have. Because, for example, here you can see the average values in the data set together with the minimum and maximum values that they get. You can immediately see that, for example, one of the Hodge numbers, H1, is strongly imbalanced, and it actually vanishes for 70% of the time. And that is a problem from the deep learning point of view. And this is one of the points that we needed to address in order to predict them. And also the variational ranges of the four Hodge numbers are very, very different. For example, H22 reaches almost 1,800, while H11 gets only to 25. So basically, we have a strong outlier problem, and we have some issues that are actually present also in machine learning literature, and there are still an open research debate also in that field. Our first approach at this point was a classification task in order to set up the stage and try to see whether we could see some particular properties we could exploit in order to predict your Hodge numbers. And in order to do this, we actually adopted a training scenario based entirely on H31. So basically, we optimized our network on only one of the Hodge numbers, and then used the same network in order to classify the others. This basically allows us to also probe the possibility to generalize one single model to predict all 4 Hodge numbers instead of having a specialized network for each of them. And it also allows us to keep the number of parameters pretty contained, and even though the accuracy is pretty high, because as you can see, of course, H11 gets almost perfect accuracy, but in this case, H11 is very, very simple to predict, but also all the other numbers start to present a good accuracies to work with, taking into account the fact that the network is not optimized for each Hodge number. This actually inspired us to start to consider the idea that one single architecture might be able to learn all the Hodge numbers at the same time. This is actually known in the literature of computer science, and it's a very interesting research area of multitask learning. So basically, the idea under multitask learning is to have a network which is able to learn different distributions at the same time. And the way we tackle the problem is through what is known as hard parameter sharing. Basically, a first block of layers which has shared parameters for all 4 Hodge numbers that we want to learn, and then a task-specific architecture for each of them. This is particularly interesting, and it's also interesting from an algebraic geometry point of view and a string theory point of view. Basically, because it strongly reduces the risk of overfitting, and it generalizes better. It also presents a very nice way to solve the problem behind outliers in the distributions. This is basically, very roughly said, what is a outlier for a certain task may be a good sample for another task. This is particularly relevant in the Hodge number predictions, because we know that the Hodge numbers are actually related. There exists a certain number of relations that actually connect the 4 Hodge numbers. For instance, the Euler characteristics is actually one of them. And also, this is one step forward in learning just one model for the entire problems, which for a string theorist is, of course, the most interesting way to tackle the problem. The architecture we came up with has different properties. It is a multitasking network, which, however, presents auxiliary branches inside the same architecture. So basically, it's a multitasking architecture for the 4 Hodge numbers, but then each Hodge number is at the same time a sub-multitasking network in order to mine as much features as we can in order to get better results. This was roughly inspired by an architecture which is known in computer vision, which is called a deep miner, which was presented also very recently at the International Computer Vision Conference. And it basically allows us to mine as much as information as we want, but also to be able to control the output by presenting by mining different representations of the same outputs. The number of parameters in this case is of course larger, because we get from less than 1 million parameters to 10 million parameters. But of course, this has to be compared to other kind of networks in the same fields, such as computer vision for the original Google Net, which has 7 million parameters, but just for a single output. Or even something in natural language processing, such as GP3, which astonishingly gets to 175 billion parameters in training. Another particular point that I want to point out is the fact that we needed some some definition of a loss function for training the model, which gave us more stability against outliers. Because of course, multitask is already a sort of regularization of the outlier problem, but we also implemented a network using what is known as Hoover loss, which basically interpolates between a quadratic and a linear behavior based on the certain hyperparameters, which we can set depending on the task. Of course, the downside of this approach is a longer training time, and for training this particular network for 300 epochs, basically the training time gets to 5 days on an NVIDIA Tesla architecture, and we were actually limited to 5 days by cluster time. So basically, we see that introducing this kind of models, this kind of computer vision models, also increases the complexity of the underlying algorithms. However, the results are extremely good, because with 80% training ratio, all 4 Hodge numbers get more than 80% accuracy without the need for outliers removal, and most importantly, without the need to rescale the Hodge numbers, for example, in the interval 0, 1. The network is actually able by itself to predict very different ranges of variation. That was actually the key feature that we were trying to achieve. Very rapidly, I would like also to show the predictions of the network and show that, for example, when we study the residuals of the network, the model is not both doesn't overfit, but also does not present a trend in the errors that it makes, which means that the model is actually statistically complete, so reliable. And of course, longer training times might also be able, in light of the learning curve that I showed before, because as you can see, the accuracy keeps rising very fast. The only problem is that, of course, using more training data also uses a lot more training time. And finally, the most important thing from the point of view of both algebraic geometry and string theory is also the fact that what we call CICY minor, so the architecture that we present, introduces different features in the architecture in order to be able to get the best accuracy. And for example, we also tried to remove the auxiliary branches that we introduced in order to mine more features. And one thing that we saw is that the absence of the auxiliary branches actually resulted in a loss of accuracy for H21, which was the particular Hodge number which was vanishing for 70% of the time. This means that basically the auxiliary branches is able to bring back a certain kind of weighted distributions in order to be able to predict the entire group of Hodge numbers, the entire set of Hodge numbers at the same time. The batch size is also a key point in the predictions, because, for example, a very large batch size leads to a loss in accuracy for H22, which is the Hodge number, which has a larger variational range, meaning that the statistics that we use in order to accelerate the training of the network need to be tuned to a certain, up to a certain amount. And finally, the other important thing is also the loss function that we introduced, which is robust against outliers, shows that, again, for H22, the accuracy is very different in case we use a normal mean squared error loss, which is actually used a lot in regression models in machine learning. Let me just point out one more point in this. We also explored the efficacy of attention models inside our model, and even though attention models are quite a thing in computer vision and natural language processing, in this case it did not lead to a better accuracy, but we saw that, for example, they led to a faster training time, because the accuracies were reached around half of the training of the entire model that we actually had at the end. So just to conclude, our work basically shows that that modern AI models are actually promising in the field of geometric deep learning, in particular for string theory and algebraic geometry, and that basically we have a lot of additional tools that we can use in order to study these kind of models. So, for example, multitask is one of them, but also exploring other loss functions and other AI techniques may shed some light on how these models work. Basically, because we know part of the theory behind the geometric data. So basically, this kind of twofold approach. So using computer vision in order to predict the quantities in algebraic geometry string theory, and at the same time using algebraic geometry string theory in order to understand how the deep learning models work, is actually beneficial and can be explored at length in this field. Finally, as an idea of how to continue, what could be the future directions? Well, the future directions are so different, and so they can go in so different directions that I wasn't actually able to find that to make a list. So I will just very briefly say that, of course, computer vision is not just the only field which we should explore for algebraic geometry string theory, but, for example, should we consider Kreutz's-Kart's list of polytopes? Of course, we could try to use graph neural networks in order to study the problem. But of course, we can also try to use other architectures based on REST nets or natural language processing methods, which are actually very much used also in knot theory in mathematics. So in a sense, they already have an interdisciplinary approach use. And finally, we could also tackle other problematics that arise in the predictions. And for example, one thing that I think might be extremely useful is to start to study how the models actually work through explainable AI systems, such as, but not limited to, Shapley values or other or tensor decomposition of the neural network weights. So of course, the work there's a lot of work to do, and with this, I thank you for the attention.